Here we go. All right, so this is the same notice. The chemicals I gave you on our warm-up quiz were not random. They are actually 3 of the pieces in this equation, right? We had lead nitrate. That was number 3 on your warm-up quiz, right? Potassium iodine, and then this one. And you showed me what these 3 things look like in water. So in this flask right here, the container says it's Ki, like this. But is it really like this? It's actually like this, right? Because it's in water, and so it actually is separated. Okay, so I'm going to mix some of this with some of this, which is this one, right? Is it really PbNO3? No, but it's PbNO3, right? So we have these things floating around, we have these 2 things floating around. We're going to pour them together and see what happens, okay? All right, so here's my lead nitrate, PbNO3. Now, obviously, for stoichiometry, I need enough of both for it to work out, but as long as I have enough of both, it's going to go, so I'm not really caring how much I measure, because I'm okay with excess. Okay, so here's my lead nitrate, here's my potassium iodine. These require, like, nothing else besides bringing them together. Everybody ready? 1, 2, 3. Right? It's our orange juice again, right? No, it's not orange juice. Okay, so we saw this one before when we talked about chemical versus a physical change. Today, we're going to really now understand how in the world this happened. Okay, and then our lab on Friday is actually going to be doing almost like, I don't even remember, like almost 30 different of these types of reactions. So a precipitation reaction will always have the same pattern, where you're starting with 2 aqueous substances, you pour them together, it gets cloudy because you created a solid. So don't be deceived, this is not a yellow liquid. It's a solid that's been stirred around because it was made as I poured it, and so it's like muddy water, right? That looks like chocolate milk. But if you let it settle, I'll show you last periods. It's not all the way settled, but here's last periods. Can you see it starting to get a little clear?
That's weird.
Okay, so as I let it sit, the powder, because of density, will settle to the bottom, and then I could use filter paper, get it out, and I have a dry sample I'll show you at the end of the powder itself. Okay, so that is the idea of a precipitation reaction. So our goal today is to look at these and to get down to what is known as a net ionic equation. Okay? All right, so our first step is knowing, or how do we know that this one is the solid that was created and it wasn't this species, right? Like, how did I know, like, that is the PbI2? The honest answer is it's really because scientists have done a lot of testing and they figured out which ionic compounds always stay together, that their bond is too strong and water can't pull them apart. So PbI2 does not break apart, it does not dissolve, it stays as a solid. So that's where this, I'll fill this in and then we'll go to the next one. This is where we have a whole list right there of solubility rules, where chemists have determined these ones are insoluble, but these ones are soluble. We are going to use the rules to help us figure out whether it's S or AQ, but you don't have to have the rules memorized. Okay, there's one little box I'll show you that we do need to know, but everything else, the AP says explicitly, like, you do not have to have them memorized. Okay? All right, everyone good if I go here? So here's our rules. So if we were testing our equation we just did, right, so the 2 things that were made were KNO3 and then PbI. So if I go to my rules right here, I can look up here, and you always are finding the negative thing on the chart. Okay, so the way to read the chart is you find the negative part of the piece. So our solid was iodine, right? So I find I minus, which is right here. It's under the category of generally soluble, but then notice except with, and lead's in the exception list. So because the thing we made was PbI, that's how I knew it was going to be insoluble and not dissolved. Now, this can be confusing, so be cautious. Once again, insoluble means it is the solid. which means we put a little S by it. Because sometimes that can be confusing because of the word solubility also starts with an S. Just don't get that definition backwards, right? So insoluble means it doesn't dissolve, and so you put a little S next to it, or possibly an L or a G. Most of the time it's an S. But. Okay, questions before we practice using the rules? Okay, now this one right here, this part of the rules, if you remember this, it almost will take care of every problem without actually having to look at that giant table. It is that if there's sodium in the problem, so if you want to write their symbols to remind you, sodium is Na. So if there's Na, if there's a K, ammonia is one of our group 1, so it's NH4+. And then nitrate we've seen a few times already, but it's NO3-. If it has any of those 4 in it, it is for sure soluble, which means it's going to be aqueous. And by default, that should mean the other thing is our precipitant. Because otherwise, if you do a reaction and both of the things are aqueous, have you done a reaction? No. Right, so it's really pointless to do it if they both end up being aqueous. Okay, let's take a look here at our first step. So the first step with doing these is we got to figure out, okay, what is being made when I mix these two things together? So we're going to learn how to finish the reaction. So the first step is the beginning is always going to be given to you. So let's write these down in this box to make an equation. So I have magnesium nitrate reacting with sodium hydroxide. They're both aqueous because that's how we always start, is with aqueous things. Now, as we said before, even though the bottle says PbNO3, right? But is it PbNO3? No, it's actually PbNO3, and just like the Ki. So the way these are working is this has positive and negative things floating around. This has positive and negative things floating around. And so then when you pour them together, the positives can find a new negative and vice versa. And you could call it what's known as a double replacement. Or, if you more fun way, it's a do-si-do, trade your partner. Okay? So Mg is the positive. So it will pair up with the negative of the other. So you always get an outside pair with the inside pair. Because could Mg ever pair up with Na? Yeah, they're both positives, right? So they're not going to pair up with each other. They have to go with the opposite charge. Okay, now, when you are figuring out how they pair up on the other side, okay, you have to do small numbers first by figuring out the charges. So before I go across the arrow, let's figure out what charges these each are coming with already. Magnesium is just an element, so to find its charge, I just go to the periodic table. Find magnesium, everybody put your finger on it for me. Oh, that's very easy. What column is it in? 2. So what charge would it have? 2. Plus 2. Yep. Okay. Now, for the thing it's with, balance your math to be neutral. So if magnesium has a plus 2 charge, and it's with 2 of these NO3 things, what charge does the NO3 have by itself? Minus 1. We want the individual charge. So keep in mind that this was plus 2. Look down here to see how many you have. Since there was 2 of them, they each need to be minus 1. Okay? In a sense, if I were to draw this out visually, because there's 1 of those, and 2 of these, right, 1 to 2, and since this was positive 2, in order for this whole thing to be 0, these each have to be minus 1. Does that make sense how I kind of like mathed it out? Okay, coming over here, sodium's an element, find it on the table. What charge does it have? And then it's paired with OH. There's only one of them. So good, and -1. Okay, questions on my charges. Okay, so step 1, find the charges. Step 2, balance the new relationship. So magnesium wants to dance with OH. It's a +2 to -1. So the new formula needs to be MgOH2. I need 2 of those to balance out one of these. Okay? Sodium is going to dance with nitrate. They're a +1, -1. So it's a nice balance there. So it'd just be NaNO3. Always write the positive one first before the negative one. That's just the formula. Okay, questions so far? Yes, Emily.
Why can't it, so like, since they're plus and minus, but they get broken up at the beginning, but then they stay together at the end, is that just because they have a stronger like force together?
Yeah, so not all of them do it. So let's do that next and figure out, of these things that were made, which one actually was made? Because one of them actually really wasn't and they didn't really even come together. So what was our 4 we said are always soluble? Okay, ready? We're going to say this in unison. Ready? So it's sodium, potassium, ammonia, and nitrogen. Okay? So this one technically has both, but as long as I see one. So since it has sodium, I know this one actually didn't really want to dance with each other in the first place, and they still stay aqueous. Okay? But this one really wanted to stay together. We can say they get married and became solid. So the difference, Emily, is there's certain substances that the force of this is stronger than the dipole of the water. And so the water actually can't break it apart anymore. Okay, any other questions? We have one more thing we actually have to do. Yeah, Ian.
If it's transition metals, then how do we know the charge?
Hold that. We'll get there. It's going to be kind of like, you just like, it's always the idea that it has to be balanced, the overall charge, and so you can kind of like reverse figure it out. Yeah, good question. Alex.
If we're balancing the equation, we need 2 sodiums.
Good. So then the final thing is we do have to make sure the overall reaction is still balanced. So you notice that, I don't know where you noticed that it needed to be fixed, but that this side started with 2 NO3s, which means we still have to end with 2 NO3s. But then if I put a 2 here, that means I also should have a 2 here. So this is the idea of like building your scoreboard and balancing both sides. Okay? Thanks, Alex, for that. Okay, so the 3 steps we went through are: number 1, find the individual charges. Individual. Okay, so we did, that was in purple. Up here, we had to find the individual charges of the pieces. Okay, we then paired them up and rebalanced their charges, right? So find new partner. Oh dear, it's hard to write and spell at the same time. Okay, so they find a new partner and you have to rebalance the charge. It's a new relationship, new charges make it balance. So find new partner and balance charges. I'm going to emphasize at that step, those are the small numbers. That means you're doing the subscripts. Right, so this is fixing the subscripts on the other side. Okay, step 3 is find your precipitant. Right, find which one is the solid. Find precipitant. We do that by using the solubility rules. And then the final piece is to balance the overall equation, and that's where the big numbers come from. So balance overall, and once again, those are our coefficients, aka the big numbers, not the small ones. A common confusion students have, so I just want to address it so maybe isn't as a confusion this year, is students saying like, oh, there's a little 2 here, and just carrying that with it over here. And like doing something like this. That marker's struggling. Right? Why do I not do that? It's not how it works. True.
Can I get a smiley face?
Right.
Because after you balance the equation, it works out so that there's like 2 and a 3.
Yeah. Tell me this, Brian. Why was there a little 2 on this side?
Because there were 2 molecules, and so on the other side, there's still 2 molecules.
The balance is still there. The difference is the reason why this is here is because of what it was with, right? It was dancing with magnesium, so it had to be balanced that way. When you change your dance partner, the only small numbers that come across are the ones that are part of the groups. So like NO3 inside the parentheses, that 3 needs to come. But numbers outside of parentheses, they don't come because they're just grouping in sets. They have to balance in the end, but they don't come with it. Okay? Okay, questions before we try another problem? Okay, let's dive down now to the molecular level and draw some pictures of our molecules and what they look like. Okay? So we hit the, what do we see with our eyes? This kind of gives you a little bit of the symbolic side. Let's get to the molecular view now. Okay? So turn to this page with me.
Fine. Oh, okay. Never mind.
Okay. What we're going to do is we're going to take, so here's our reaction again. This is the same one I did with the demo. Here's your overall. In these boxes, we're going to draw a molecular view of what it looks like inside that flask, right? So if we can magic school bus down to the size of these molecules, what would we see in each of these flasks? Okay? So if you want to maybe draw an arrow, I don't know, did they light it better on your notes than they did on the PowerPoint? Not really. So if you want to draw a little arrow around you, so this box is going to represent this substance. This box is going to represent this substance, Ki, and then our final box is when I poured them together. So both of these. So these are kind of like RB4, right? Draw these, then draw this. Okay, before and after. Okay, so PbNO3, 2, it's written like that as a molecule, but at the molecular level, what would I see? They're going to be apart, right? So it's not PbNO3 that I draw in here. I draw Pb2 plus and 2 NO3 minuses chilling out in the water. Now, we're not going to draw water in our picture for these problems because it doesn't apply. Obviously, on the AP test, that would be a very logical, like, A, B, C, or D type question where eventually that would come in, right? Where you would maybe, hey, how does water interact with these things? And you draw your Mickey Mouses again. But in our case, that doesn't matter for our problems, okay? All right, so we have PbNO3. This one is our Ki. How's that one gonna look? Magic school bus in there? Apart, okay? We have K plus, I minus. Now, in order for this reaction to work, I can't just draw one. Because the balance equation says I need a 1-to-2 ratio, okay? So I need to have at least one more. But would it be wrong to draw a third? Yeah, you can have once again to emphasize the difference of the balanced equation tells you how it's going to change, but it doesn't tell you what's actually in the beaker, right? Whatever's in the beaker is what I chose to pour in there. And in this case, we chose to pour more Ki than we needed for our lead night. Okay? All right, we poured these two friends together, and what happened?
Magic.
Magic. Who found each other as their soulmate? Yeah, so PB paired up with I and became a solid. So the way we're going to draw that on this side is we're going to draw it as a little clump. That's our solid. We'll say it's settled already. We're going to label it as our PB. Oh, why did I do a capital? PB. Oh my goodness. I2. Right, so our lead iodine. Right, when I poured them together, this one found two of those and stayed together because their bond is so strong. Okay, so I'm going to kind of, this one paired up with these ones. Okay? What about the K and NO3s? What did they do?
They just kind of float there.
They just are there, right? So we just need to draw them there still, but they didn't really ever come together. So we need to draw our NO3s and our Ks. Yep, so we also should show the I that didn't have anything to bond with. Right, it's still going to be there. So we would consider that, right, this is like, we had excess Ki to start with. And so there might be some excess I still that didn't get used. If I did it in a perfect stoichiometric amount, then you wouldn't have the excess. But okay, questions on my pictures? Okay, in this box, do you have a box like right here with this?
Yes.
Yeah. Okay, we're just going to simply, this is like a visual way to see it. We're just going to write the equation in what is called its complete equation, which is really like the true form of the substances. And I keep doing it with my hands today, whether are they really like this or are they actually like this? Because the overall reaction is going to show everything with something. But we know it's not really that way. So this is like the real picture of what's going on. Yeah, yeah.
So the PBI, the PBI2 label is positive.
It's a great question. No, because as a solid, we don't show their charges. Yeah, good question. So it's just PBI2. Okay, so our complete equation is, instead of, so if you want to compare to the overall, it's not really PbNO3, it's really Pb2 plus and 2 NO3 minuses. So we're just putting a symbol to our pictures here to show, hey, this is really what's going on. So then, in our overall equation, it showed 2 Ki, but it's not really Ki, it's actually K and I, so we're going to show that as separate things. So 2 Ki pluses and 2 I minuses. Then what it really made was, it did make PbI2, but did we actually make KNO3? No, we made K and NO3 floating around together, right? So we're going to show that as K plus NO3 minus. Yeah, Alex.
Would that be 2K plus and 2 NO3?
Oh, thank you. Good catch. Got to keep it balanced, because we had it balanced before, so don't unbalance it as you keep going, right? Thanks, Alex. That was my piece of that. Okay. Soraya, I think it was you. How did you describe what K and NO3 are doing in our final one?
Floating there.
They're just floating there, right? Did they actually play a role in making my beautiful yellow powder?
No.
Doesn't appear so. We call these things spectator ions. They're just watching the game happen. But they actually didn't play a role. That's what should go on this blank here. in creating the substance. So our final step is to write something known as the net ionic equation, which gets rid of the spectators. Okay, I'm gonna write down here. Can people in the back, can you see this little thing? I write it right here. You should have another box right there to write it in. So this is known as the net ionic equation. So who's spectating this party? Yeah, potassium and iodine. Notice on the, rewind. Iodine is not spectating. She found her soulmate. Okay, nitrate is spectating, because notice, so 2 Ks floating around, the Ks are still floating around, right? NO3s are floating around, they're still floating around. So my net ionic equation would be Pb2 plus reacting with 2 I minuses to make PbI2 solid. Make sure it's very small, but charges are a must when they're ions. Because if I take this away, you're now talking about solid lead metal, which is not what our reaction is about at all. So don't leave off charges, even though they seem like a minor detail. Symbolically, molecularly, they're everything. Okay, questions before we try another one? Just a little bit faster, but same process. Okay, turn the page and let's try this again. Oh, I guess here's some blanks to fill in, sorry. So the net ionic equation, once again, shows us kind of the main things that got involved in the process. And then like we mentioned, if it turns out that everybody's spectating, it means you didn't have a reaction at all. So if we pour the 2 things together, it would stay clear. Okay, everybody ready? Okay, before we do this one, and we're going to take a 1-minute stand-up stretch break. Stand up, get a stretch in.
Stand up. Stand up, camera.
Go.
Okay, back down you go.
If it was 5 minutes, I'd go.
I wonder how far that would stretch. Like you went from here to the commons,
I can try it.
through the ceiling, and then like through the sidewalk right here.
I can try it real
That's pretty
quick.
close to a floor. What do you think?
Do his act.
I can try it.
I feel like from here to there, it's about 100. This is
Let's
maybe a little
pause
short.
class.
I guess
This
it's
is,
a little.
we need to make a scientific discovery.
We might have to go through the outside walls, not the lights. That could be pretty close. You go like 400 schools. See how fast I'm going?
So, do I need to test this?
We might.
Do like thick binders.
I've actually been wondering, read this
And
article
I
about
like
this.
slice like
I don't really have my
with like
training.
8 different papers. So it was super exciting.
We don't have time for that. Like, quick little one. He's like, this is good for your brain, right? Right? We can like talk about something characters.
Look.
Okay, here we go, friends.
Everyone there?
Grab your pencil, let's do this. Alright, so our reaction says barium chloride is reacting with potassium sulfate. Okay, so barium chloride reacting with potassium sulfate. Our goal is to get to the net ionic equation. Okay, so you always have to start with the overall, because you have to know like what's happening to begin with, if it doesn't give it to you. Okay, so just like we did before, step 1 is we gotta know the individual charges of each of our things. So I'll give you a second to write those out, and then we'll do the charges. Okay, so going up here, so barium, find out the periodic table, its charges, good, +2 charge. Okay, Now, technically, chlorine is just an element, so you could find it on the periodic table and find its charge, but you can also find it through, you know it has to be balanced. And so if barium has a +2 charge and there's 2 chlorines in the compound, each individual chlorine must be a -1. But that also follows the pattern that chlorine has 7 valence electrons, and so it only wants 1 more. Okay? All right, coming to this one, potassium has a +1 charge. It's in our first column. And then SO4, since I have 2 of these +1s, a single SO4 must have 2 minus.
Get it, y'all.
By the end, you might by default just start memorizing the charges, not because you even tried, but you just start using them enough, you just know what they are. But once again, you can always figure it out from the periodic table. Okay, so on the other side, who's barium going to dance with? And look, they're +2, -2, how nice. So BaSO4, and then K is going to pair up with Cl. They're a +1, -1, so they're also a happy balance.
So the charge is changed.
Yep, because the charge just cancels, so you don't have to like change the ratio.
Do they have to be K2 and Cl2?
Great question, Lily. So this is where we don't want to carry the subscripts over because those were there because of what they were paired with before. Those 2's will come into play when we balance the overall reaction, so we don't want to forget about them, but don't carry them over. I'm glad you brought that up, Lily. Have a smiley face for that. Okay, so that was step 1, balance the new charges. Now we got to figure out who stays together and who actually just is still there. So, say it with me. What are the ones that are always aqueous? Sodium, potassium, ammonium, and
Nitrate.
so in this case, potassium. So I know that this one is going to be aqueous. And so this one must be my precipitant. Final piece before we move on to the next equation is what Lily brought up. We do have to make sure the overall equation is balanced. And so since I started with 2 chlorines on this side, I still must have had them at the end, same thing like with the potassium, so it works out. So I gotta balance with the coefficients. Yep, that's it. Everything else is balanced. Okay, questions with my overall reaction, where something came from, where it's going. Okay, we're now going to write the complete reaction, which is like, once again, kind of the molecular view of are these things as they are written or are they actually apart? Okay, so if it is aqueous, then that means it's not really BaCl2, it's actually going to be Ba2 plus and 2 Cl minuses. The nice thing is if you do the charges on this first step, it then makes it like go faster after that. Okay? In this molecule, it's also aqueous, so it's really going to be 2 K pluses and SO4 2 minus. So once again, I'm showing them in their true form of what they look like. What do I do with the BaSO4? That one stays together. Why? They like each other, right? The solids don't break apart, right? It stays as a solid, as you can see in our beaker, right? It just stays together, okay? But this one's aqueous, so it is going to break apart. Big numbers distribute to both. So we have 2 K pluses and 2 Cl minuses. So that is my complete reaction, which gives us a better picture of what's really going on in our flask. Yeah, say that.
Is the complete the net ionic equation?
Not yet. So the last one, the net ionic equation, is when we get rid of spectators.
Excuse.
Yeah, Garrett.
On a test, would you have to write like the overall, the complete and the ionic?
No. So that's the hope, is that you can eventually just go from here to here. I'll show you, there are some complicated problems where you can't skip this because it's just too hard to. But most of the ones on your homework, if you can see how to go from here to here, do it that way. I've never seen it where it's like required to do that middle step. Good observation. Okay, so who's spectating our game here, our dance? Yep, so potassium, right? Notice they're the same on both sides. And chlorine. So our net ionic equation, you'd write Ba2 plus SO4 2 minus to make BaSO4. And that's our final answer. Questions before we try one for some smileys? Okay, Jack.
Do you want us to write all three of those on our homework?
Nope. If you can just do this this and this, that's fine with me.
Okay.
Okay, I'll give you 4 minutes. Work with your table. Try, I don't know the number. Exercise right below it. 4 point something B. 4.2B. Try that one out and then we'll see how we're doing.
Let's do minus. So what do we do here? That's crazy. That's so crazy. Oh yeah. That's that.
So here's the problem.
So the charge for
You're right.
is plus 1.
I don't know if it's right.
So that's plus 1. There's 2 of them. That's the 2 minus.
That's the liquid. So there's 2 of them. They're both plus. It's 2 plus. It's just 2.
No, I think it's like one of
Yeah, that's the difference. So it's only one element, but the number applies to it, and it's like one of the weird rules. If that makes sense. I see. Good job.
Balance, you know.
Well, two CO2 minus or CO2 negative.
Yes, I mean technically how you have it written, it is balanced. It's just CO3, like if you come up here, like the charge it has here is the charge it's always going to have. And so CO3 doesn't exist as a 1 minus thing. Like that just doesn't exist. It's always
NaCl.
charge is kind of like part of its identity, so even if it like goes and bonds somewhere else, its individual charge never changes. Yes. Yep.
I think I can make it.
I think he was because it's illegal.
Looks like a few people are still working. If I checked it off and you're good, if you want to start on the homework while you're waiting, you can do that.
Yeah, baby.
And then we'll do the tricky one in the
What are the smiley faces looking like though? Let's go. Let's go.
No, you can also get smiley faces. Good job, guys. Have a smiley face. How are you doing, Sophie? It is. It's perfect. Okay. Yeah. It's that, so like you balance their charges, right, which was +1, -1, but it's that whole thing of like, you can't, matter can be created or destroyed. And so if originally you started with 2 sodiums, there still have to have been 2 in the
I need
end.
to finish looking like simplified round.
Yep, exactly. Does that make sense? Not a dumb price.
Hold on, let me get you writing. Oh. Oh, that was it. That was tough. Oh. I need to take notes. Exactly. No, dude.
Everyone watching at home, remember to like and subscribe. Comment.
Become a member to receive exclusive chemistry labs. Join the Patreon. Join the Discord. Playing grades for about weeks now, and I just keep getting enough of it. All these heroes are like, it's just so much I've been playing lesbian since it came into the game, and it's so bad. It's been a lot of fun. It's been a lot of fun playing with them. Oh, where's the boat? Anyways, thank you for sponsoring this video. Let's get back on the content.
I need to take notes, teacher? Say less. Say less, Miss Sophie. Let me go check.
So everyone at home is just sitting there listening to us idiots. It's like, is there going to be more chemistry?
It's just so starting on Friday.
News flash, there's not more chemistry.
We better not work on Saturday.
Yeah.
Good. I hope I work on Monday.
Please subscribe.
Hey, nobody.
I don't know.
Sit there and just be like.
Yeah, actually, you should go to Discord.
Take turns eating noodles. Very open about getting paid. You want to take a
Go ahead. I got the cards for the next 20 minutes. Go ahead.
Oh, that's okay. It does look similar though.
Bring your head down. Easy 30, 45 minutes. You won't even. No.
Alright, we just got a few minutes left here. Well done, everybody. Looks like we're all there, and the few little mistakes we made were getting fixed. Close your mouth really quick. Okay, so tonight's homework, 4.2, there's a front and back side. It's just this exact process. Some of them I do have you draw pictures just to get the visual side of it. The others are just writing the equations. There's one more problem in our notes that we didn't get, where it is still a net ionic equation. It just gets a little bit looking more complicated, because this is a great example of how the AP test will take a topic you do understand as students. Like, I know you understand it. But then they ask it to you in a way that is like, that doesn't look the same. And so then we short circuit and shut down and don't know what to do. But the process really is still the same. The difference is, and this kind of goes with what Garrett asked, when you see a reaction that says to write the net ionic equation, if you have more than two things, you're gonna have to do the complete step. Because it's not as simple to just cut down. With this one, and we'll solve it next time because we don't have enough time to solve it right now, but I want you to point out something, and this will pick us up where we left off. Where's my precipitant? It's my water. Right? This reaction was in water, but then it made water. Right? Now, a common thing, so this was a question that was on a test a few years ago, and the common mistake I saw is students skipping and saying, oh, well, if water's my precipitant and water's H2O, then my net must be HO, H2O. And they claim that as their net. The problem is, if I look on the left side, these two pieces aren't they're individually. So there's a little bit more to it. So we'll finish this next time, and then we'll do our lab all about it.